All right, so let's see here. Chemistry 3101. Today we're continuing on with Chapter 5, and we looked at this slide at the very end of our last lecture, and we just want to differentiate between enantiomers, diastereomers, and determine what the difference is between those. So at the beginning of Chapter 5, we discussed isomers, and way back in Chapter 2, we discussed what constitutional isomers are, and I told you that that's something that you are probably introduced to even in general chemistry. And the main topic of this chapter is stereoisomers, right? We're talking about compounds that are having the same connectivity, however, they are non-superimposable. Thank you. But if you have stereoisomers, there are actually two subcategories of stereoisomers. Now, last class, we looked at enantiomers in a lot of detail. Enantiomers are mirror images that are non-superimposable, like your right and left hand, for example. And then we introduced the concept of diastereomers. So these are not superimposable compounds that have the same connectivity, and they're also not mirror images. So to summarize, enantiomers are stereoisomers that are mirror images, and diastereomers are stereoisomers that are not mirror images. And again, I recommended memorizing these two definitions for the next quiz. All right, so let's take a look at an example of some diastereomers. Now, earlier on, we talked about these two compounds, these two alkenes, cis-2-butene and trans-2-butene, and we discussed why this is called cis. It's because we have two groups that are identical on the same side of the molecule, and we discussed why this molecule is trans, because we have two groups that are identical on opposite sides of the double bond. So these molecules are stereoisomers, right? They both have the same connectivity. If you were to write a condensed formula for either of these, you would just have this, right? The condensed formula doesn't differentiate between the cis and the trans stereoisomers. So again, these are stereoisomers, but they are not mirror images. If you draw a mirror plane in between the two, you can see that there is no, that they are not mirror images, and so therefore they are diastereomers of each other. Remember that enantiomers have identical physical properties like densities, melting points, boiling points, and so forth. But diastereomers will have different physical properties. Why? Because physical properties are a result of intermolecular forces between molecules. And you can clearly see that if I have two or more molecules of cis-2-butene interacting with each other, they're going to interact with each other or pack together differently than two or more molecules of trans-2-butene. So again, diastereomers will have different physical properties, different boiling points, different densities, so on and so forth. Well, let's expand this definition of diastereomers and take a look at it from the point of view of chiral centers. So if you have a cyclohexane, right, you guys all know what cyclohexane is. If you have a cyclohexane with three substituents, like I have shown here in this circle, okay, we have three stereocenters in this molecule. We have one here, we have one here, and we have one here. So the three stereocenters, if we assign their relative stereochemical configurations, we have 1R, 2R, and 3S, right? That's the configuration of the three chiral centers. 1, 2, 3. So we have R, R, and S. Now, if I invert each one of those stereocenters, right? If I convert the R to an S, if I convert this S to, or sorry, this R to an S, and this S to an R, then I have made an enantiomer, right? And we discussed that during the last class. We said if you want to draw the enantiomer of a compound that has one chiral center, all you do is switch the dash to a wedge or the wedge to a dash, right? And so the same thing here. All you do is switch R for S and S for R. So the relationship between these two compounds here is these are enantiomers. These are enantiomers of each other. If you look at any of the pairs of compounds in the green boxes, you'll see that these two compounds are enantiomers, these two compounds are enantiomers, and these two compounds are enantiomers. So with this cyclohexane with three substituents, we have three pairs of enantiomers. Now again, I'm just rehashing the same thing, but if you don't follow me, let's just pick one at random. We'll pick the last one down here. Why are these two compounds enantiomers? Because every single stereocenter has been inverted. The wedge has been turned to a dash. This dash and this dash have both been turned to wedges. Even if you didn't have a drawing of the compound and you just had the name of the compound, you'd see that all of these stereocenters have been converted from R or S, respectively, into S or R. So again, that's the relationship between enantiomers. They're non-superimposable mirror images. We switch dashes to wedges, and we switch R's to S's, right? So there's 8 possible total stereoisomers. And then it says also consider the relationship between enantiomers and diastereomers. So if I just go back to this first compound right here, okay, how many diastereomers are there to this compound? Well, I know that this compound here is an enantiomer, so it is not a diastereomer. But if you look at any of the other compounds, you can see that each one of them is a diastereomer of this compound. So it has 1, 2, 3, 4, 5, 6 diastereomers. And we could do the same thing for any one of the compounds in here. So every compound in here has 1 enantiomer and 6 diastereomers. Now, if you're like, I'm not sure that these are diastereomers, let's just compare the relationship between 2 of these at random. So we'll take this one in the yellow circle, and I'll just pick, I don't know, let's pick this one for fun, okay? Well, how do I know that these are diastereomers? Remember, they're stereoisomers that are not mirror images. So in order for them to be mirror images, every dash will have to be converted to a wedge, and every wedge would have to be converted to a dash. Look, you can see that this stereocenter has the same configuration, whereas these two are different. Therefore, these are diastereomers. Looked at from the viewpoint of R and S, we could do the same thing. All right, all we have to do is analyze. We have 1R, 2R, 3S. This one has remained unchanged, whereas these two are changed, and therefore, again, these are diastereomers. So we've looked at several different ways of deciding when we have enantiomers and when we have diastereomers. So with the amount of talking I did about that, you can clearly see that it's really important that you understand the concept of enantiomers and diastereomers. It's going to come up a lot in organic chemistry. Well, what if you had a compound with a lot of stereocenters? Okay, it says the maximum number of stereoisomers that you can have for an achiral compound is you take the number of chirality centers and you take 2 and you put that to the power of that number of chirality centers. Okay, so the maximum number of stereoisomers that we can have is 2 to the power of n, the number of chiral centers. So if we look at the molecule cholesterol, you could try this at home. You can erase what I'm going to write here, but you can see that it has 1, 2, 3, 4, 5, 6, 7, 8 stereocenters in the molecule. Remember, if you're like, oh, I'm having a hard time deciding what's a stereocenter, remember, you're going to avoid anything that's a CH3, right? You're going to avoid those because that's not a stereocenter. And anything that's a CH2, you're going to avoid that. Any carbon with a double bond on it, anything that's sp2 hybridized, you would ignore that. And anything that's sp3, you would ignore those because none of these carbons could be stereocenters because none of them could have 4 different groups attached to them. Okay, that's kind of a quick rule. So you can rule out things like, okay, I can rule out this carbon and this carbon, right, because they're sp2 hybridized. Anyhow, just a quick rule there for you. Anyhow, so the total number of the total number of stereocenters in this compound is 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So we have n is equal to 8. So the total maximum number of stereoisomers would be 2 to the power of 8, which is 256. So that means there's 256 total possible stereoisomers of cholesterol. One of them would be an enantiomer. So out of the 256, only one of them would be the enantiomer of this compound. If you want to draw it, all you'd have to do is flip the dashes to wedges and the wedges to dashes. You're done. Okay? And every other stereoisomer would be a diastereomer. Now, our bodies only make this one compound. We only make this one stereoisomer. So you can see how the body is pretty good at synthesizing chiral compounds and asymmetric centers. Anyhow, let's take a look at some compounds and see if we can decide whether the compounds are enantiomers, whether they're non-superimposable mirror images, or whether they are diastereomers, stereoisomers that are not mirror images. So I'll ask you about A. Does anybody have a feeling about A? Would these be enantiomers or diastereomers? they're enantiomers. How did my students answer that so quickly? The reason they knew that is because when I want to draw an enantiomer of a compound, what would I do? I take this wedge, I convert it to a dash. I take this dash and I convert it to a wedge. So these two compounds are clearly enantiomers. Another option, and some students like to do stuff like this, if you were to take this molecule here, and if you were to rotate it around this axis, like that, if you were to rotate it 180 degrees, what you would end up with would be a molecule that looks like this. So this bond that's facing down would now be facing up, like this, and this one would be facing down. And you can see that these two are mirror images of each other. That's actually a more difficult treatment, but you know, some people like to manipulate everything in their mind that way, and there's no problem with that at all. What about the next one? Does anybody have a feeling about the next one? What would these be? They would be diastereomers, absolutely. Yeah, these are diastereomers, stereomers. Yeah, why? Because only one stereocenter has been inverted, the other one is the same. The next one is a little bit trickier, right? C is a little bit trickier because you'd have to manipulate this bond here. You'd have to rotate this bond and put the methyl in the plane with this methyl group, or you could put the chlorine pointing out like the chlorine there, and then you could evaluate whether these are enantiomers or diastereomers. Let's do that first. So if you were to rotate that sigma bond so that you had something that looked like this with the methyl group coming out like this, look, if you have the hydroxyl pointing up, and again, this is where handheld models would come in really handy, okay? If this chlorine is pointing in the plane, and then you have a hydrogen in the back like this, if I put this methyl group, if I rotate it so the methyl group is in the plane, I mean this methyl group so that it's in the plane like that, okay? What's going to happen is that the chlorine is going to be, sorry, I'm just thinking here. The chlorine is going to be going back like this, and then the hydrogen is going to be coming out like this. And so these compounds would be diastereomers because they have one stereocenter that's the same, and then they have one that's the opposite configuration. If you find that difficult, let me show you a way that I think is even easier when you're starting learning this, and that would be just to assign the stereochemistry, the RRS configuration to each one of the stereocenters. So if we start with this stereocenter right here, this is going to be my highest priority group. I have a hydrogen that is in the back. That is going to be the lowest priority. This carbon is going to be the second highest priority because it's attached to a chlorine. This one is only attached to 3 hydrogens. So I have from 1 to 2 to 3. So going like this, my hydrogen is in the back. Therefore, this stereocenter is R. So let's erase some of this stuff here. We've assigned that stereocenter as R. Let's take a look at the next one. We have our hydrogen in back, so we're kind of lucky there. The chlorine is going to have the highest priority. The hydrogen has the next highest priority. This carbon, look, is attached to an oxygen, a carbon, and a hydrogen. This carbon is attached to hydrogen, hydrogen, hydrogen. So this one is going to be the second highest priority. This will be the third highest, so we're going in this direction, which is clockwise. And so that stereocenter will also be R. Let me just write that in here. So we have another R. So we have R and R, right? Okay. Well, now let's take a look at the next one. The first one has an R configuration for the same reason it did the first time, right? You go from 1, you have the hydrogen in the back, which is lowest priority. This carbon is going to be second highest because it's attached to a chlorine, a carbon, and a hydrogen. Again, this one is attached to hydrogen, hydrogen, hydrogen. So this should be the tiebreaker. So let me delete some of that. Okay. Oops. There we go. So this will be second highest priority. This is third highest priority, going like this, clockwise. This stereocenter is R. And if we look at this stereocenter here, we go from the chlorine, which is highest priority. The hydrogen is the lowest priority. This carbon is going to be the second highest priority. Why? Because it's attached to an oxygen. This one is a lowly methyl group attached to 3 hydrogens. So we go from 1 to 2 to 3, going like this. That's counterclockwise, and my hydrogen is in the back. And so this stereocenter would be S. So I have what? I've got RR and I have RS. And since they differ at one of the stereocenters, but the other one is identical, they're not enantiomers, but they are stereoisomers. Therefore, these two compounds are diastereomers. Stereomers, like that. There we go. All right, well, let's move on from there and talk about section 5.6, which discusses symmetry and chirality. So there's some quick rules here that you can use to determine when a compound is achiral. When it comes to determining whether a compound is chiral or not, it gets a little bit more difficult, but our book only looks at, we don't get into examples that are overly complex. So let's take a look here. It says, any compound that's got one chirality center is chiral. Well, that's not too bad, right? If you have a molecule that's got just one measly stereocenter in it, if it's R or S, there you go. You've got a chiral compound, my friend. So here's something that you might not have thought of, and I hope you all read the textbook before coming to class today. If you've got more than one chiral center, the compound may or it may not be chiral, okay? Depending on the situation. Now, you're like, how would a compound have more than one chiral center and be an achiral molecule? Well, I'm going to show you why that is, okay? First, let's take a look at these two compounds here and talk about the types of symmetry that are in these compounds. So it says, if we look at these compounds, they both have two chirality centers. Now, we discussed chirality centers last class, so I'm not going to go over it in a lot of detail, but I have a chirality center here and here, and then I have one here and I have one here. Okay, I've got the trans 1,2-dimethyl cyclohexane and cis 1,2-dimethyl cyclohexane. All right, so I've got these two compounds. They both have two chirality centers. Well, I'm going to tell you that one of these compounds is chiral overall and the other one isn't, and I'm going to explain to you why. Okay, it says the trans isomer is chiral, but the cis isomer isn't. Okay, again, they both have two chiral centers, right? They have that in common, but this compound is chiral, okay, meaning it will rotate plane polarized light. We discussed that last class. And this compound is achiral. It's not going to rotate plane polarized light. The reason why the second compound, the cis 1,2-dimethyl cyclohexane, is achiral is because it has a plane of symmetry running through the molecule. Notice the word plane of symmetry, okay? Because you might think, oh, there's some symmetry here. What if I rotate that? You know, there's some symmetry. But there's no plane of symmetry. There's nowhere that I could draw a mirror plane through this molecule and I get reflectional symmetry, right? If I have a mirror plane here, you can clearly see that both sides would be superimposable on each other. Okay, and so the rule is this. It says the cis isomer has a plane of symmetry, which means it's going to be superimposable on its mirror image inside the molecule. Okay, so the plane of symmetry is inside the molecule, and therefore it's not a chiral compound. Okay, so the rule is this. When a molecule has a plane of symmetry, it's going to be achiral. This would also be another good rule to memorize. In our book, it doesn't say, oh, memorize this rule or anything like that. But I've taught the class long enough to know that it's handy to have that memorized before you really grow accustomed to looking at molecules that are have a plane of symmetry and saying, okay, well, that's an achiral molecule. Well, these achiral molecules, based off of their plane of symmetry, they have a special name. Okay, there's a special name that we use to describe them. We call them meso compounds. So it says molecules with an even number of chirality centers that have a plane of symmetry are called meso compounds. So again, you've got chiral centers in the molecule, but since you have a plane of symmetry, we call it a meso compound. All right, another way to test if a compound is meso is see if it's identical to its mirror image. So that would work too. And the mirror image of the cis isomer shows that it can be superimposed. By definition, when a compound is identical to its mirror image, it's not chiral, achiral. So anything that's identical to its mirror image is not going to be chiral. Well, I want to discuss, and this isn't covered in my slides, but I want to discuss why this compound, a meso compound, why it would be an achiral compound. So if we go back here and we take a look at the two stereocenters in the molecule, okay? I have a stereocenter here and I have a stereocenter here. Well, if we look at those two stereocenters, since they're mirror images of each other, they're going to have opposite configurations, right? One of them will be R, one of them will be S. So what that means is that one of them is going to rotate the plane polarized light in one direction, right? A chiral center will rotate plane polarized light, but the other one is going to rotate it in an equal and opposite amount in the opposite direction, okay? And so they're essentially cancel each other out. Now, again, that's not covered in our textbook, but if you wanted to know, like, why the heck doesn't a meso compound rotate plane polarized light, in other words, why isn't it chiral? It's because the two chiral centers are opposite in configuration, and so they do both rotate plane polarized light. Absolutely they do, but they cancel each other out the same way that a racemic mixture cancels each other out, okay, except it's inside the molecule, so it's a meso compound, all right? Again, you got to know the definition of a meso compound. You've got to be able to recognize meso compounds, and if you need practice on that, which anybody would learning the subject, if you look at the practice problems that I have suggested, there's a whole list of them on Canvas. I've definitely chosen some problems from the textbook that cover symmetry and chirality in terms of meso compounds. So again, if the compound has a plane of symmetry, it's achiral. It says meso compounds also have less than the predicted number of stereoisomers based on the formula that we learned today. Right? If you look at this diol here, we call it a diol because it's got two alcohols in the same molecule. We've got a chiral center here and a chiral center here. So remember, the formula was the maximum number of stereoisomers was 2 to the power of n, which would be 2 squared, which equals 4. But if you draw out all of those stereoisomers, you'll see that 2 of them are identical, right? You see that 2 of these compounds are identical. Now, if you're wondering, why are these 2 compounds identical? Well, if you take this molecule and you flip it over here, you can see that both of those dashes would become wedges. And you can see that those are both the same compound. Why? Because this is a meso compound, right? It's a meso compound. Why? We've already covered this. It's because we have a chiral center here and we have a chiral center here, but we have a plane of symmetry running down the molecule. All right, there we go. So let's take a look at this question here. This is question 5.24. It says, draw all possible stereoisomers for each of the following compounds. Each possible stereoisomer should only be drawn once. So we have this 1,2-dimethyl cyclohexane derivative in A. How many chiral centers are there in this molecule? Could anybody tell me? Yeah, thanks, Kayla. There's 2. Absolutely. Yeah. You're all 100% correct. Look, right away, we could eliminate anything that's a methylene, a CH2. We could eliminate those. We can eliminate a CH3. So those are eliminated. The only 2 possibilities left over are these 2 methynes here, right? A CH is called the methine. And those are both chiral centers. Now, if you're really behind, if you're really struggling with this, let's just take a look at one of them. Okay, we have a hydrogen. Remember, a chiral carbon is one that is attached to 4 different groups. We've got a hydrogen, we've got a methyl, we've got a methylene here, and we have a methine. So those are clearly 4 different groups. So that's a stereocenter, and the other one is a stereocenter for the exact same reason. So again, I have a stereocenter here, and I have a stereocenter here. Well, let's start by analyzing the maximum number of stereoisomers we could have, which would be 2 to the power of n, which would be 2 to the power of 2, which is equal to 4. So that's the maximum number. It doesn't mean we're going to have 4 possible stereoisomers, but the maximum number we could have would be 4. Well, let's start drawing some out. What if I drew it in such a way that I had one of the methyl groups pointing up and the other one pointing down, like that? There's nothing wrong with that compound at all. And what if I invert both of those stereocenters, right? Now, this is something that we looked at earlier today. If you invert both of those stereocenters, you end up with a pair of enantiomers, right? These 2 compounds are enantiomers, right? Non-superimposable mirror images of one another. If you don't believe me that these are mirror images, Just rotate this 180 degrees, and you'll see that you'll end up with the mirror image of this molecule. Again, this is where handheld models can come in really handy, no pun intended. What if I put both of the methyl groups on the same face of the molecule, like this? Well, you might be saying, well, I could invert both of those stereocenters too. Absolutely we can. Let's do it. If we invert both of those stereocenters, okay, we see that these two are the same compound, aren't they? Why? Because they're a meso compound, right? This is a meso compound. And so I'll cross this compound out because it's the exact same as the compound that's drawn above it. And so the total number of stereoisomers in this case would be 3. Maybe I'll leave that one there, okay? Yeah, maybe I'll just leave it right next to identic. Shoot. Where am I going here? I'll say meso 2. I'll just leave it up there just in case anybody's confused on the subject. The next one is very similar. It's just not a cyclic molecule. We have a stereocenter here and here. So the maximum number of stereoisomers would be 2 to the power of 2, which would be 4. So I can start by drawing the carbon skeleton. Let me divide the page here so you don't get confused. There we go. So if I draw the carbon skeleton, I can put one of the hydroxyls going up, the other one going down. I can draw the enantiomer of that compound with one going down and one going up. Again, this is a great opportunity for handheld models. Okay, if you rotate this 180 degrees, you'll see that these two compounds are enantiomers. If you analyze the chirality at their stereocenters as being RS, you'll see that one is RS and the other one is SR. And then the last compound, if you draw both of the hydroxyls on a wedge, let's say, this is going to be a meso compound, right? Because I have a stereocenter here. I also have one here, but I have a plane of symmetry. Plane of symmetry. Therefore, this is a meso compound, right? Plane of symmetry with chiral centers, right? Okay, so I have a meso compound. And so I could draw this compound, right, where I have both of those hydroxyls on a dash, but that's the exact same thing as the meso compound. Okay, so I have a total number of 3 stereoisomers in both examples. So 3 stereoisomers each. All right, give me a thumbs up if you follow me on that, and if it makes sense to you, at least some sense. Part of the way. Yeah. Okay, and you'll find that manipulating molecules in your mind is a skill that can be developed. Okay, so don't think, oh, I don't see it right away. Well, just like when we looked at Newman projections, remember back in chapter 2, we looked at Newman projections. Everybody is able to train their mind's eye to look at Newman projections and be able to draw them correctly. And the same thing with stereochemistry. In fact, one of my colleagues admitted to me one time, he said, you know, stereochemistry is something I really struggled with as a student. He said, I found it really, really difficult. And I said, well, how did you figure it out? And he said, persistence. You know, I just sat down and worked at it until I got it, right? So, again, being able to manipulate things in or molecules or objects in your mind's eye is easier for some people than others. But I promise you, it is a skill that can be developed and improved and mastered. All right, let's move on to section 5.7. 5.7 deals with Fischer projections. Fischer projections can also be used to represent molecules with chirality centers. If any of you have studied biology before, you might have seen a Fischer projection of glucose per se. You know, you might have seen something like this in your biology textbooks. I don't know. Maybe yeah, maybe no. Okay, if you draw this molecule here, this is called D-glucose, which is what we call a hexose. And in organic chemistry too, we do a whole chapter that deals with carbohydrate chemistry. And the reason that Fischer projections exist is not just to make your life miserable and teach you something else. The reason these exist, okay, is because when Emil Fischer was studying carbohydrates, he was trying to assign the structures of all the different carbohydrates. And there, many carbohydrates depending on the number of stereocenters. And so he needed a quick way to draw these molecules and represent all of the stereocenters without drawing a bunch of dashes and wedges. So actually, Fischer projections are actually much simpler for looking at sugars, for carbohydrates, with multiple chirality centers than if we just draw them with dashes and wedges. Now, our book doesn't even draw any sugars with dashes and wedges. They definitely don't in this chapter, and I can't remember if they do in the carbohydrates chapter. But if you just do a quick Google search, you could look up the structure of D-glucose with dashes and wedges, and you're like, oh, that's way more complicated, okay, to think about. Anyhow, so the horizontal lines in a Fischer projection are coming out of the page, like they're coming out to hug you. Like if you stretch your arms out, it was my students who taught me that, by the way. The first class I ever taught at UCCS, they said, oh yeah, it's like the bonds are hugging you. I said, okay, that works, all right. Anyhow, and the vertical lines are going back into the page. So what do you notice about this stereocenter here? You notice that the lowest priority group, right, which is the hydrogen, is coming towards you. Remember that when we use the Kahn-Ingold pre-log rules, the lowest priority group is supposed to be facing away from us. But remember that I also taught you a trick last class, that if the lowest priority group is coming towards you, you evaluate what the stereochemical configuration would be, and then you reverse it. Okay, so we're going to do the exact same thing here. Okay, exact same thing. So let's say we wanted to assign the stereochemical configuration of this chiral center right here. Well, we're going to start with the oxygen, that's highest priority. Then we're going to go to the hydrogen, which is lowest priority. Between methyl and ethyl, if you haven't figured it out already, if you haven't tried any of the practice problems, if you're just dealing with a linear chain, for example, so say you have, something like this versus something like that, the longer the chain is, the higher the priority. That's a quick and dirty rule, and you can use the laundry list to prove me right on that. But the longer the chain, the higher the priority it is. Remember, that works for linear chains. When we have branched chains, it won't necessarily work. So you have to be careful. But if they're just linear, the longer they are, the higher priority they have. So we're going to go from 1 to 2 to 3. Then we do the dance around the chiral center. So we go from 1 to 2 to 3. So that's going clockwise, which would be R. And since our hydrogen is coming out in front, we reverse it. And so the stereochemistry here would be S. All right, so let's see here. Fischer projections are really useful. We're going to use them a lot in the carbohydrates chapter. And here you can see in the first one, we call this a tetros because it's got 1, 2, 3, 4 carbons in it, tetros. The next one is a pentose, and this one is a hexose. Anyhow, that's neither here nor there for today. All we're worried about is the chirality centers. You know what I'd like to do? I hadn't planned on doing this, but we got time. Let's try. Could you guys assign that chiral center? Could anybody do that? I'll give you a second to look at it and try it instead of just hollering at you. Just take a minute, and if you can figure that one out, see if you can figure this one out too, and then we'll move on to the next slide where we look at the relationships between Fischer projections. If anybody has the first one, the one in red, just type it out. That. Let's see. Oh boy, I got 2 students who gave me an answer and they're both right. I love it when my students are right. Okay, puts a big smile on my face. That's great. Both of you are absolutely correct. So look, how did my students figure that out so quickly? They said, okay, it's attached to a hydrogen, a hydroxyl, all of the spinach here and all that. So there's definitely 4 unique groups. The oxygen has the highest atomic number, so it's going to be number 1. Hydrogen is number 2. I have a carbon here and I have a carbon up top. This carbon in the aldehyde is attached to oxygen, oxygen, hydrogen. This carbon is attached to oxygen, carbon, hydrogen. Remember, we list them in order of atomic number, right? So my tiebreaker is going to be this one right here, the oxygen. So that means that the carbon at the top is going to be the third highest priority. Shit, did I write a number 2 or I meant to write a number 4? Pardon my language. Okay. Anyhow, this will be group number 2. There we go. And this will be group number 3. So watch carefully. Okay, I'm going to get Green highlighter. Okay, we start on number 1. We go from 1 to 2 to 3, like that. What are we doing? We're going counterclockwise. But remember, this hydrogen is on a wedge. So we're going to reverse that. So instead of being S, this stereo center is in fact an R configuration. Okay, again, we could try the next one. I'll do it a little quicker, the next one, because you guys are probably faster than me at this by now. Anyhow, so we have the oxygen, which is highest priority. We have the hydrogen, which is lower priority. If we look at this carbon here, it's attached to oxygen, hydrogen, and hydrogen. If we look at this carbon here, it's attached to oxygen, carbon, and hydrogen. This is my tiebreaker. So this carbon is going to be group number 2, and this one down here is going to have priority number 3. Let's get the old green highlighter out. We're going from 1 to 2. Sorry. Yeah, there we go. We're going from 1 to 2 to 3 like this, which is clockwise. But again, the hydrogen is on a wedge. Okay, not that big. It's on a wedge. Okay, so instead of being R, that stereo center is S. Okay, there we go. S. All right, so that's how you do it. Okay, let's move on. Fischer projections are really great. Okay, the first job I ever had in the chemistry lab, I was an undergraduate in my 3rd year of university in a chemistry degree, and I worked with a carbohydrate chemist. So I spent a lot of time looking at Fischer projections and looking at chairs of sugars, you know, which have an oxygen in the ring. Anyhow, that's for another day. But anyhow, Fischer projections are so great at assessing stereoisomeric relationships, right? You look at these two here, you can clearly see that both of these stereocenters are inverted, right? You can clearly see that they're mirror images, they're enantiomers. These two are stereoisomers, right? Because this stereocenter has been reversed, but they're not mirror images, therefore they're diastereomers. I mean, Fischer projections are just so powerful. You know, it's kind of the kind of thing you wish you had invented yourself, you know? All right, anyhow, let's try a couple more and see if my students can assign some chirality centers here. So let's see. I want you guys to try this one. Well, there's only 2 here, and this one. So give it a second. We'll call the first one's A, and the second one is B. So if you have an answer, throw it in the chat. Just write A is this one, B is that one. And I will definitely ask you a question like this on your quiz on Monday. Just look at a molecule, or 2 or 3. What are the stereochemical configurations? So you can try both of them. All right. Thanks, Skylar. Good. Yeah, okay. Well, this is the answer that 2 of my students put in the chat pretty quickly. Is one of them said that A is R and B is S, and the other person agreed. Okay, so they said that A is R and B is S. Let's take a look at the first one, A. The nitrogen has the highest atomic number, so it's group number 1. The hydrogen is the loser. If we look at this carbon, you can clearly see its higher priority. It's attached to an oxygen, oxygen, oxygen. And this carbon is attached to an oxygen, hydrogen, hydrogen. Here is my tiebreaker. And so this group is going to have the second highest priority, and this one will be third. Look, we grab the green highlighter. We go from 1 to 2 to 3, like that. That is counterclockwise. Remember, we reverse it because the hydrogen is coming out towards us. Counterclockwise is S, and so this stereo center is R. So this looks perfectly good to me. Let's take a look at the next one. Let me do some erasing here, maybe. That out of the way. There we go. Okay, so if we look at this one, the oxygen is going to be highest priority. The hydrogen is going to be lowest priority. this carbon is attached to oxygen, oxygen, hydrogen. Why? Because each bond in the double bond counts as a single bond to oxygen. Okay, there we go. And this carbon is a lowly methyl group. It's attached to hydrogen, 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 right? The methyl is always the loser, right? So the oxygen is our tiebreaker. So we have this group being second highest priority, this one being third. So we go from 1 to 2 to 3 like that, which would be clockwise, which would be R. But again, since our hydrogen is horizontal, we reverse it. And so the stereochemical configuration here is S. So my students were right on both accounts. Excellent work, you guys. Okay. And you should be able to do those relatively quickly. Mr. Dion is not a speed guy. Definitely not. I'm not the fastest at assigning stereochemical configurations. It's better to have it correct than do it too fast and get it wrong. Anyhow, so a couple of years ago, what year is this? 2021. So a couple of years ago, one of my colleagues was on a sabbatical for a while, and I was teaching organic chemistry for chemistry major. So I was teaching this class, but going into a lot more detail. And we were discussing this part of the book. Now, normally we don't ask a whole lot of questions about this in Chemistry 3101 to the point where you could almost skip it, but I don't want to because it's so interesting. Okay, my students and I, we get in a really long discussion about this one day about conformationally mobile compounds, and I just want to share this with you because I think you'll find it really fascinating because it goes all the way back to Newman projections and something that you probably never thought of, and I didn't think, believe me, I didn't think of it when I was a student, really that sharp. Okay, but if you think about a butane molecule, right? Just plain old butane. Okay, I could draw my butane maybe a little prettier. Anyhow, and if you look down this bond, right, and you look at the Newman projection of butane, if you look at the two gauche conformations of butane, these two here, okay, which you know are in equilibrium with each other. Remember the lecture where I taught you Newman projections and I was holding up the models and spinning them around in front of the camera or whatever? So you know that there's free rotation around this sigma bond. So you know that these are in equilibrium with each other. But something that I never thought about when I was a student, okay, until somebody shared it with me, is that these conformations are chiral, okay? They're mirror images. Now, again, they are in equilibrium with each other, but if you just draw a mirror plane, you can clearly see that they're mirror images, okay? So we call these rotomers, okay? And because these rotomers are interchangeable by rotation around that sigma bond, it's not a chiral compound, right? Butane is obviously not a chiral compound. If you're like, come on, Mr. Dion, you taught me that a methyl isn't chiral and a methylene isn't chiral. There's no way this could be chiral. You're right. But what's interesting is that if you cool the molecule enough, so if you bring it down to a low enough temperature, you can isolate, you know, one of these conformers or rotomers over the other. Okay. Yeah. So something you might not have thought about before. And if you look at, let's say, chair conformation of cis 1,2-dimethyl cyclohexane, you know, you have the structure drawn down here. You see it's got a plane of symmetry. It's a meso compound, right? Nothing new under the sun there. But if you look at the chair conformation, and if you look at these two conformations, you see that there is a mirror image there. So the two conformations are enantiomers. Okay, so I just thought it would be really interesting to share it with you, and I thought that some of you who are really interested in the subject might find this fascinating, that you can have a compound that's completely achiral, but actual conformations of the compound can be chiral. So kind of interesting. Anyhow, I usually don't ask my students a whole hell of a lot about this. It's not the easiest thing in the world for some students to understand, but it is really interesting, maybe worth the value of, you know, one multiple choice question if I was to show you two conformations, and I would set the question up in such a way that you would, you know, wouldn't be lost in the bushes or anything. Sections 5.9 and 5.10. So 5.9 deals with chiral molecules that don't have chirality centers, so something called atropisomers. If you want to take the time to read that, it'll take you, what, depending on, you guys can probably all read faster than me. Takes me probably 7 minutes, so it'll take you 3.5, right? And also, there's always some student who's like, how do you separate enantiomers? How would you, if you have a mixture of R and S, a racemic mixture, how do you separate them? And that would be a really good question. And the answer is there's a couple of ways you can do it. And section 5.10 discusses that. So if you wanted to know how to separate enantiomers, there are ways to do it. I've done it myself, okay? I've also hired people to do it for me. Yeah, no kidding. I've actually hired chemists to do that for me a couple times. Anyhow, so let me just put this bug in your ear. If I ever skip a section, it's because it's not covered on the ACS final. Dr. Anderson doesn't cover it, and I don't cover it, right? We have to have some kind of a gentleman's agreement because it wouldn't be fair if one class at UCCS covered a whole bunch of content and then another class didn't, right? That would not be fair to our students. However, let me just throw this out there to you. If you have an inquiring mind, and you want to learn more about organic chemistry, you can just peruse these sections. Just read them quickly. It'll only take you 15 minutes of your day. You learn something a little extra, and yeah, there you go. Anyhow, just encouraging you to learn more about the subject and really develop a love for organic chemistry. All right, anyhow, the last section, and we have lots of time to cover this, deals with E and Z designations of alkenes. Remember that we talked about cis and trans alkenes? We talked about that quite a bit. Well, sometimes you can't denote an alkene that has different substituents as cis and trans, right? In order to denote an alkene as cis or trans, you've got to have two groups that are identical on the two vinylic carbons, right? You'd have to have two X's or call them two Y's like this, right? You have to have groups that are identical in order to say, okay, well, these are cis and these are trans. Well, if you look at this molecule here and this molecule, neither of them is cis or trans, but it's got 4 different groups, and these are 2 diastereomers, aren't they? Right? They're stereoisomers and they're not mirror images. So how the hell would we differentiate between the two here? Cis or trans doesn't work. Okay, there's no like group on each of the carbons. So what do? Is we use something called E and Z designation. Does it say here? Yeah, so E stands for entgegen, which is opposite in German, and Z is for zusammen, which is together. Anyhow, so here's how you do it. You guys remember the Kahn-Ingold Prelog rules, CIP rules that we learned last class, and we've applied them several times today. You use the exact same rules to give priority of groups on the vinylic carbon. So if you look at this carbon here, you evaluate these two groups. Look, fluorine has a higher atomic number than carbon, therefore the fluorine has higher priority. On the other carbon, this vinylic carbon, nitrogen has a higher atomic number than hydrogen, therefore it gets priority. Since the two highest priority groups are on the same side of the molecule, we call this a Z alkene, zusammen, or together, okay? So again, if the top priority groups are on the same side of the molecule, it's Z for zusammen, which means together. And my students taught me this too. Students come up with some great stuff. They said if the groups are on opposite sides, we call them E, which actually means entgegen, but they called it opposite. I don't know. Just sometimes my students will say stuff that they use to remember things, and I can't get it out of my head, So any mnemonic that you can find to help you remember things is a good thing. It really is. Okay. Where was I? So if you look at this alkene here, you see the nitrogen and the fluorine are on opposite sides, and so it's an E alkene. Again, here, these are on the same side, and so we have a Z alkene. That's all there is to it. Again, we use the exact same rules that we used for assigning stereochemical configuration. So this question asks us, for each of the following alkenes, assign the configuration of the double bond as being E or Z. So we have this one here and this one here. Maybe I'll do the second one. So if we look at the first one, okay, what are the 4 substituents? Well, we've got this isobutyl here. We've got an isopropyl here. We've got butyl here, and then we have a hydrogen. All right, so we have all of those groups. All right. Well, let's start by looking at this carbon here. If we want to decide between the isopropyl and the butyl, it might be a knee-jerk reaction to say, well, the butyl's got more carbons, it's going to be higher priority. Remember, I told you that only works for linear chains, okay? This is branched, right? An isopropyl is not linear. It goes off in this direction and this direction. That's not a straight line. So what do? We make our laundry list. this carbon is attached to a carbon, carbon, and a hydrogen, right? CCH. And this carbon is attached to a carbon, hydrogen, and hydrogen. So carbon, hydrogen, hydrogen. And so the tiebreaker is going to be this one here. So isopropyl is higher priority. Now the next carbon is a little bit simpler, I think, because it's got a hydrogen attached to it, which has the lowest atomic number on the entire periodic table, and then it's got a carbon attached to it. So clearly, the isobutyl group is going to be higher priority. So could anybody tell me, would this be an E or a Z alkene? And it's not a trick. Yeah, thanks, Skylar. It's an E alkene, absolutely. So this is an E alkene. Why? Because the two highest priority groups are on opposite sides of the double bond, right? One is on this side, and the other one is on this side. So we can call this X, and we can call this Y, like that. Okay? All right, there we go. Let's take a look at the next one. I'll give you a second, and if anybody could tell me if the next one is E or Z, that would be just great. Give you a second to think about it. Yeah, there we go. My students are all saying that it's Z. Okay, well, let's take a look at the first carbon. It's attached to a chlorine and a carbon. Well, chlorine is obviously higher priority, so we'll circle that one. And the other carbon has a hydrogen, which is always the lowest priority, and a methyl group, which has a carbon directly attached to it. So we'll put this, since those are on the same side of the double bond, this is a Zusammen, or a Z alkene. All right. There you have it, my friends. That's all there is to it. That's all she wrote. Okay. Just give me a second here. I had some practice problems I wanted to take a look at. What we could do is we could stack it like all right, so let me just go to a blank document here. Let's see. Give me a second here. Give me 2 shakes of a lamb's tail. In the meantime, while I'm doing this, so I've spoken to a couple students in the class who are interested in writing the MCAT exam, which is the Mcat, which is the entrance exam for medical school. And something that I learned about from a good friend of mine who wrote the Mcat a couple of summers ago is she turned me on to this thing called the Mcat Podcast. So if you go on podcasts on Apple, and Mr. Dion is not the expert on podcasts, I don't listen to them myself, but if you go under podcasts, let me see here, under my library, you have something called the Mcat Podcast. So it's literally called the MCAT Podcast. Oops, what the heck is that? There we go. And that podcast is amazing. It covers everything to do with the MCAT. It explains how long the exam is, what the subject matter is, the kind of questions that they ask. It covers like literally everything about the MCAT. And something that the reason I thought of that is because when here when I was talking about having a mnemonic for remembering different things in a chemistry class, like E for EPICID or whatever, things like that, just silly things that my students come up with, which aren't silly, they're in fact wonderful. The MCAT podcast, they actually have a discussion between 2 medical doctors, and they're both saying how they rely on mnemonics all the time for remembering things. So it's definitely a useful a useful thing. Anyhow, can you guys see my blank page right now? Can everybody see my blank page?
Yeah.
Okay, good. All right. There we go. All right. There we go. Well, let's try some problems where we assign stereochemical configurations. I'm going to write a few compounds out here, and you guys give it the old college try. So just bear with me here. You know, I'm going to try to draw neatly. In fact, you know what? Let me draw it a little bit bigger since you're probably looking at it on a little screen. So in that case, let me take my watch off, which keeps bumping up against my iPad. All right, there we go. When I first started in graduate school, my supervisor said, oh, we're going to have a meeting and everybody's going to present their work. So here you go. There's the first stereo center. Give that one a try. So yeah, he said we're going to have a meeting and everybody's going to present what they're working on and stuff. And anyhow, I stepped up to the chalkboard. I mean, this was 1999. I got up there and grabbed the chalk and I was like, just watch me. I was slinging the arrows and the bonds were flying and all kinds of structures being drawn. And I was doing like this, you know, drawing stuff like this. And my supervisor said, like, whoa, 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 slow down, man. He's like, can you take some time and draw your structures neatly? So, you know, if you're a good organic chemist, you should try to draw your structures neatly. Now, that kind of throws myself under the bus, doesn't it? Because sometimes I draw a little too quickly. All right. Anyhow, but he said, you know, a good organic chemist should draw structures neatly. And then I went to a conference where I saw a guy named Barry Trost. You can Google him if you want. So Barry Trost, who's a really famous organic chemist. And he gave a presentation in front of 1,000 people just using the chalkboard, and it was pretty amazing. And to see this guy draw structures so quickly and so neatly, it was really, really fun. Anyhow, all right, I'll give you a second to look at these three, and we'll call them, I don't know, we'll call them A, we'll call this one B, and we'll call this one C. Let's see if you can come up with an answer for any of them, and you can type it into the chat. All right. You can see my students are blasting through it. Skylar, I'm going to give everybody else a little more time. Skylar, if you finish those, you could try this one maybe. Try this one. So if we have a methyl group here, a methyl group here. Give that one a shot. All right. Thanks, Stephanie. Looks good. All right, I'll give it a couple more minutes because I know that there's differing levels. You know, stereochemistry is not a quick thing. Some people it takes a little bit longer. All right, well, I said that, and now I want to take a look at A. Let's just go over it slowly, okay? Because some people find this, you know, pretty challenging. And if you're struggling or whatever, there's no problem. You know, that's what we're here for. We're here to learn. So let's take a look. Okay, yeah, I see my students are coming up with really good quality answers. Absolutely. You're all in the right vein. Skylar, Josh, Stephanie are all in the right vein. Let's take a look at A together. Let's do it nice and slow, okay? First thing I noticed about that stereo center, it doesn't have a hydrogen attached to it, does it? But remember, the lowest priority group is going to be behind us, okay? So there's a couple of ways that we could tackle this one, and I'm going to copy the whole thing because I think I'm going to need more room. There we go. So copy. I'm going to move it down here. So I have lots of space to draw. Okay, here we go. Okay, if we look at that stereo center, our highest priority group is going to be the oxygen, isn't it? Right? Now, if I make a laundry list, this carbon in my methyl group is attached to hydrogen, hydrogen, hydrogen. You probably guessed that that's going to be the lowest priority, right? If you look at what an ethyl group is, okay, and I know you all know what an ethyl group is, right? We have CH2, CH3. Now, if you need to draw that out, no problem. So this carbon is attached to carbon, hydrogen, hydrogen. And this carbon here is also attached to carbon, hydrogen, hydrogen. So there's no tiebreaker between these two carbons. So we have to keep going. Now, if we go one more carbon, you can see that the methyl is attached to hydrogen, hydrogen, hydrogen. And this carbon here is attached to oxygen, oxygen, carbon. And so the tiebreaker is going to be this oxygen right here. And so all of this group here, that's going to be the second highest priority. So I have my group number 2 here, and I'm going to erase this and just draw ethyl again, just to simplify it, ethyl like that. And that's going to be priority number 3. Now, here's where it gets interesting. You've got a couple of options here. You can either rotate this bond, okay, so that you put the methyl up here, right? We can do that. Now, if we do that, if we put the methyl group up there, and I'm just going to draw it over here, what you would end up with is this. So we have 1, 2, 3, 4, 5. We have our carbonyl here, okay? If the methyl moves up in the back, okay, like this, okay, then our hydroxyl is going to be in front, like this, and our ethyl group is going to be down here, okay, when we rotate that bond. So now our lowest priority group is going behind us. If we number these 1, 2, 3, and 4, like this, we see that we're going from 1 to 2 to 3 to 4, which is S. All of my students said that that stereocenter was S, so there's got to be some power in numbers, right? And so the stereochemical configuration is S. Okay, are you ready for it? There is another option, okay? Now, this is for people who are really good at manipulating the stereocenter, or manipulating the molecule in their mind. This is how I would have done it, okay? So I would have done it like this. Just erase all this spinach. So if I call this 1 and I call this 3. The way that I would have done it is I would have imagined myself looking at the molecule from up here, just like God, you know, looking down from above, okay? I would imagine myself looking down that bond. What would I see, right? What would I see then? The methyl group would be pointing in the back. I'd have all of this stuff, right, down here. I'd have the ethyl group over here, and I'd have, nope, sorry, I put the ethyl group on the wrong side. I'd have the ethyl group over here, and I'd have the hydroxyl here like that. So I would go from 1 to 2 to 3 like this. So you'd be going like this, which would be counterclockwise, which is S. Okay? Did anybody else do it that way? Or did everybody do the rotation trick? Anybody else do it that way? Where you imagine yourself looking down. So you're basically looking down this carbon-carbon bond right here. No? Okay. Anyhow, that is an option, okay? And you'll find that the more you practice, the better you'll get at it. All right. Anyhow, let's take a look at the next one. This is called 2-aminobutane. And I see that a couple of my students put that this one was S. We can do this one a little quicker. We have a hydrogen coming out in front here. The nitrogen has the highest atomic number. Hydrogen is lowest. Look, here we have an ethyl group, and here we have a methyl group. I told you that when you have a linear chain, the longer that it is, the higher priority it will be. So this will be number 2, and this will be number 3. If we follow the order, we go from 1 to 2 to 3, like this, going around the chiral center. That's clockwise, which would be R, but since our hydrogen is on a wedge, we're going to reverse it, and so this stereocenter is S, like that. Let's try C. Same thing. We have one chiral center. Here our hydrogen is coming out in front. So no matter what the stereochemical configuration we get is, we're going to reverse it, right? That's the trick we're going to use. Fluorine has an atomic number of 9, so it definitely is the highest. Hydrogen is the lowest. If we look at this carbon here, it's attached to a carbon, carbon, and a hydrogen, right? C, and this hydrogen. Whereas this carbon is attached to this carbon and 1, 2 hydrogen. So carbon, hydrogen, hydrogen. The tiebreaker is going to be this carbon right here. And so this isopropyl group is going to have a higher priority than this group. Oops, I meant to put number 3 there, didn't I? Than this group right there. So if I follow the order going around the stereocenter, I go from 1, 2 to 3 like that, which is counterclockwise, which would be S. And so I reverse it, and this stereocenter would be R, like that. Okay, there we go. All righty. In the interest of time, let's try the last one. Did anybody get the last one? This one here, the Fischer projection, because you will be asked to assign stereochemical configurations of. So somebody says, Skylar says S and S. All right, let's give it a try. So if we look at the first stereocenter, the hydrogen is going to be lowest priority, the oxygen is going to be highest priority. This carbon here is attached to oxygen, carbon, hydrogen, and this one is attached to 3 hydrogen. So this is going to be second highest priority. This will be third. So we go from 1 to 2 to 3, which would be R. The hydrogen is horizontal, therefore we reverse the stereochemical configuration. So it's S. Okay, so we're good on that one. There we go. And for the next one, we're going to do the exact same exercise. Here's our chiral center. This is our lowest priority. This is our highest priority. We already decided that this would be second and this would be third. So you go from 1 to 2 to 3, which is R. But again, the hydrogen is horizontal. And so this one is also S. So there you go. All right. In the interest of time, we're kind of running out of time. We got 6 minutes left. I wanted to go. I'm not sure how to project our textbook onto shoot. Well, here we go. I'm not sure how to project our textbook and be able to write on it because I don't have a PDF of it, but I do have a PDF of the old version of the textbook, which I cannot share, by the way. But anyhow, I have a PDF of the old version of the textbook, and it's very similar to our version of the textbook. And I want to show you some of the concepts that I want you to have down pat for the quiz. He's doing this. I don't know why it does that. No, it won't let me rifle through it. Really, it won't. Come on. Jesus. Okay. Come on. Am I really asking something that difficult? Mr. Dion has lots of patience for human beings, but very little for computers. Where I basically have none. Human beings are flawed individuals. Okay, whereas computers were created by man to do whatever the hell I want. Okay, here we go. So, son of a... Okay, let me just open up our textbook, and I won't be able to project it. But problems that I consider really important problems would be things like, and I have our textbook open right now. Give me a sec. Since we didn't have a ton of time, questions like 5.36. Okay, and I'm not saying that this is the only thing that's important, but where you have to determine the relationship between two compounds. Are they constitutional isomers? Are they stereoisomers? Are they diastereomers? Are they enantiomers? Right? You need to be able to determine those. A question like 5.37, of course, is worth the value of probably one question, where I just give you a molecule and ask you to determine the number of stereocenters or how many stereoisomers. So you have to know the formula 2 to the power of n. What else? Draw the enantiomer. Well, there's no drawing, but you should be able to recognize an enantiomer. So switch all the dashes to wedges. Of course, you need to know questions like 5.39, which is the one we just worked on. Assigning R and S, that of course is one of the major things that we look at in the class. Again, questions like 5.44, where you just have a couple of compounds and you determine, are they enantiomers, diastereomers, whatever constitutional isomers. That's a big thing in our chapter. Fischer projections. So in question 5.47, it asks you to determine the relative configuration of all these different stereocenters in a Fischer projection. So that's really important. What else? Being able to manipulate Newman projections. Newman projections could show up in on the quiz. Like you see some Newman projections in question 5.51. What else? You can see that there's like not Avogadro's number, but there's many questions where it says determine the relationship of the compounds. So a lot of questions like that, where you have to be able to look at compounds and just evaluate, you know. Question 5.55 is also a good one. It says, just tell me, is the compound chiral or achiral? Right? I think that's a really good one. So you're looking for planes of symmetry in a molecule. In fact, I think that 5.55 is a great exercise in being able to manipulate molecules in your mind. But it's kind of like the beginner stage of it, where you're able to look at a molecule and say, okay, does it have a mirror image? Like, for example, if you look at 5.55 C and D. So 5.55 C and D, where you have two compounds that look very similar. One of them is chiral and one of them is achiral, and it's not really abundantly clear by looking at the conformation that they have drawn. So I would say that that is really important. What else? Yeah, so that doesn't cover it all, of course, but those are some of the high points, and I knew we wouldn't have time to get to, that many practice questions. Anyhow, question 5.60, I'm not going to ask you how to do that. Those do show the wedge and dash drawings of some sugars and ask you to draw a Fischer projection. I won't get you to do that. Anyhow, all right, there you go. Well, I hope you find that useful. And again, the best way to prepare for a quiz is to do all of the practice problems in the back of the book, and also be sure that you understand what you're doing, right? I know I keep telling you this, but there's a big difference between doing the problems or seeing somebody else like me or maybe somebody on the internet solve the problems and having them make sense, and then you being able to do it yourself, right? There's a big gulf between there. So make sure that you understand what you're doing. Anyhow, I hope you found this chapter interesting. Again, I'm going to put together the quiz over the weekend, and I will post an announcement to Canvas, which should show up in your email as well, with all the directions. Okay, this is just a reminder that when you're using Respondus Lockdown Browser, that you have to show me your entire environment, and you're supposed to be alone in your room, okay? So nobody else in the room while you're writing the exam, and I recommend writing them at the university if you can. Anyhow, it's 9:15, and I'm not supposed to go past 9:15, and I have class in 10 minutes. So I wish you all a really good weekend and happy studying.